Hello everyone, this is Mrinal Kanti Roy Choudhury. The title of the talk is Homogeneous and Non-Homogeneous Cantor Sets, Uniform and Non-Uniform Cantor Distributions. First, let me tell you what is homogeneous Cantor set and what is non-homogeneous Cantor set. Let S1 and S2 be two contractive similarity mappings on R such that S1 of x is small s1 x and S2x equals small s2x plus 1 minus S2 for all x belongs to R, where S1 and S2 lie between 0 and 1. Then there exists a unique non-empty compact subset C of R, which is called the limit set or the invariant set of the iterated function system this, such that C satisfies this condition. Such a set C generated by the IFS this, where the contractive ratios S1 and S2 are such that 0 less than S1 plus S2 less than 1 is called a Cantor set. If the two similarity ratios are equal, that is, if S1 equal to S2, then C is called a homogeneous Cantor set. Otherwise, it is called a non-homogeneous Cantor set. The Cantor set C generated by the IFS this, when S1 equal to S2 equal to 1/3, is called the classical Cantor set, or sometimes in the literature is referred to as D Cantor set. Now, what is uniform and what is non-uniform Cantor distribution? Let C be the Cantor set generated by an IFS this with similarity ratios S1 S2 such that S1x equal to this and S2x equal to S2x plus 1 minus S2 for all x belongs to R, where S1 S2 satisfy this condition and 0 less than S1 plus S2 less than 1. Let P1 comma P2 be a probability vector, that is 0 less than P1 comma P2 less than 1. That is P1 lies between 0 and 1 and also P2 lies between 0 and 1 and their sum is 1. Then there exists a unique Borel probability measure P on R such that P satisfies this condition, where P circle SI inverse here denotes the image measure of P with respect to SI for I equal to 1, 2. And for more details, one can see this paper, Hutchinson's paper, Fractals and Self-Similarity, published in Indiana University Journal. Then there exists a unique Borel probability measure P on R such that P satisfies this, where P circle SI inverse denotes the image measure of P with respect to SI for I equal to 1, 2. Such a P has support the Cantor set C generated by the iterated function system this. If it satisfies P1 over S1 equal to P2 over S2, then the probability measure P is called a uniform Cantor distribution on R with support C. Otherwise, P is called a non-uniform Cantor distribution on R with support C. Here, I am going to give you two examples. Let C be the Cantor set generated by the IFS this such that S1x equal to 1/3 x and S2x equal to 1/3 x plus 2/3. Define the probability measure P on R such that P equal to this. Then as P1 over S1 equal to P2 over S2, here P1 is 1/2, P2 over 1/2, P2 is also 1/2, S1 is 1/3, S2 is 1/3. So these two ratios are equal here. Because of that, we call P a uniform Cantor distribution on R, which support the Cantor set C. Let C be the Cantor set generated by the IFS this such that S1x equal 1/4 x and S2x 1/2 x plus 1/2. Notice that here the similarity ratios are 1/4 and 1/2. So in this case, C is a non-homogeneous Cantor set. Now define the probability measure P on R such that P equal to this. So here you get small s1 is 1/4, small s2 is 1/2, small p1 is 1/4, and small s2 is 3 over, small p2 is 3 over 4. Then notice that p1 over s1 is not equal to p2 over s2. Therefore, here P is a non-uniform Cantor distribution on R, which support the Cantor set C. And if you would like to read a paper in this regard, you can have a look on this paper. Quantization and centroidal Voronoi oscillations for probability measures on dyadic Cantor sets. It is published in Journal of Fractal Geometry in 2017. Thank you for listening.